Hello, everyone. This is my paper for WACV 2025, HEX Hierarchical Emergence Exploitation in Self-Supervised Algorithms. And I will get the laser pointer. So the basic premise of this work is that recent work has demonstrated that SSL representations naturally organize in a hierarchical manner. So you can see at the beginning of training, all the embeddings of all the images are sort of randomly dispersed. But as training goes through different epochs, by the end of training, you get these sort of emergence of different structures that are reliably organized into different hierarchical groupings. So the question is, can we exploit this gradual hierarchical emergence to improve the training of self-supervised algorithms? So in order to answer this question, we first have to understand, how does traditional SSL optimization work? Basically, the premise of these algorithms is to counter global dimensional collapse. And the idea here is that if you have a batch of images with positives and negatives and augmentations and whatever else you have within your specific SSL method, the point of the algorithm is to prevent all of the embeddings of each one of these images from mapping to the same point. And by preventing them from mapping to the same point, you contribute to higher feature diversity, which is why higher dimensionality is a desirable property for training SSL optimization algorithms. But the reality is that this global optimization objective does not consider the existence of possible localized relationships. So what I mean by localized relationships are subsets of images or data points that share features in common with each other. For example, this flamingo and this spoonbill share the common characteristics of a bird, while this clownfish and this shark share the common characteristics of a fish. Um, so the question, though, is, why do these localized relationships matter? The reason they matter is because the previous SSL methods stop global collapse of their representations, but they don't really have any mechanism to counter the existence of local collapse. And the reason local collapse could exist is because birds such as flamingos and spoonbill share features in common with each other. It might be possible for the algorithm to map them to the same exact point, and in which case the bird superclass wouldn't have any feature diversity in order to differentiate it between different classes within the same hierarchical grouping. And the same thing for the fish superclass. So ideally, we would be able to prevent collapse both at a local level and a global level, where local collapse refers to a subset of images from different classes mapped into the same representation, while global collapse is all images from the dataset mapped to the same representation. And we proposed this view of prevented collapse from a hex regularization point of view. So then, okay, if local collapse and global collapse is important, how can we potentially exploit the emergence of hierarchical structures in order to regularize both at a global and local level? So the way we do this is that, as we talked about early in training, points are distributed randomly, but later in training, hierarchical structures emerge. So what if we introduce some regularization term during training that changes during training to add additional regularization as we gain more confidence about the hierarchical structure of a representation space? And this is what we call HEX, Hierarchical Emergence Exploitation, which, in other words, as hierarchies emerge, we want to prevent collapse of their hierarchical structures, so we can induce additional regularization to specifically target potential local collapse. So this raises a few questions. The first one is, can we sort of intuitively understand why we should introduce this local regularization? And the way we are going to show this is, we have this plot, and on the x-axis you can see epochs of training for an NNCLR algorithm. On the y-axis you see the effective rank, which is a way of measuring dimensionality. And you can see that samples drawn from the same superclass of a backbone model trained with NNCLR have a lower dimensionality than samples just drawn randomly from the dataset. This indicates that the samples from the same superclass have a greater amount of dimensional collapse. However, when we introduce our hex regularization, you can see we counter this local dimensional collapse as well as a global dimensional collapse for both random subsets as well as subsets drawn from the same superclass. So the next question is, okay, if we know that local regularization is good to prevent local collapse, how can we estimate this during training? So it would ideally we would have access to all the labels that indicate the hierarchy of our data set, but in practice this doesn't exist and we need to estimate it. So what we are showing here is the cosine similarity distribution of all the data points in the test set at different epochs of training. And we're divided it into two graphs where we show the cosine similarity distribution of samples from the same superclass and samples drawn from just sort of randomly around the data set. And as you can see that as training progresses and as training progresses for both the regular and the superclass samples, the cosine similarity values gradually decrease. But you can see that the tails of the superclass distribution are more reliably separable from those of the tails of the regular class distribution. So what this potentially indicates that if we appropriately threshold our cosine similarity distribution, we can identify samples that belong to the same hierarchy, in which case we can then target those samples for regulated local collapse. And that's exactly what our method does. We have a batch of images, we generate embeddings for these images, and then from these embeddings, we compute the cosine similarity distribution, which we then apply an epsilon threshold. This epsilon threshold is adaptively computed based on the 95% quantile of the cosine similarity distribution. And we're going to use this threshold to separate the samples into hierarchical negatives and regular negatives. Then we apply a weighted function, which is essentially just a way of upweighting these samples. And then through this weighted function, we produce our HEX loss, which is effectively decomposed in the denominator of the traditional contrastive loss into a hierarchical weighted set of negatives and a regular set of negatives that are treated in a traditional manner. So when we add HEX, we see performance improvements across many different SSL methods on Cypher 100 in this plot. We also note that if we add HEX as a regularization term with an alpha parameter on top of dimension contrastive approaches such as Vikreg and Barlow twins, and we choose this alpha parameter appropriately, we can get performance improvements by using HEX as well. We also note that HEX has consistent performance improvement across a variety of data sets. We see the effect of fine-tuning on top of Imagenet representations for many fine-grained recognition data sets, such as CARS and Caltech 101. And we also see that we have performance improvement on the traditional Imagenet setting for different methods, and as well as an Imagenet semi-supervised with fine-tune on 1% of available labels. So in conclusion, we propose an SSL method that identifies the existence of local hierarchical groupings of images and that can introduce a local hierarchical regularization term into the training process that works with a variety of SSL approaches. And we also introduce an epsilon threshold term during the training process that can be used to reflect the growing hierarchical organization of the representation space. And these are our links. Thank you for listening, and I hope that you have a great WACV 2025.